Bismillah Rahman Rahim. I hope you guys would be doing fine. And today we are here again with another interesting lecture of mechanical vibrations. And today we would be discussing the vibration isolation. That is, how to isolate the surroundings from the machinery which is vibrating. On the slide, you see two pictures. One picture is about the automobile engine. Let's say this automobile engine is vibrating, and that vibration, that vibration is transmitting into the body of the automobile or into the chassis. So first, it would transmit on the onto the chassis into the chassis of the automobile because the engine is mounted on the chassis, and then that vibration would be transmitted to the whole body of the automobile. So how to isolate the chassis of this automobile from the vibration of the engine? Here, as we discussed early, that in the engine the vibration would be harmonic. So here the harmonic excitation force is there. So the excitation force is harmonic force. So what, and the question is, what is the force transmitted to the chassis or frame of an automobile? Here you could see a rotating machinery, and let's say that rotating machinery is vibrating because of rotation unbalance. Then that vibration of the machine would be transmitting, it is actually transmitting to the foundation. So how much force is transmitted to the foundation? Actually, we are interested in that because once we know the amount of force which is transmitting into the foundation or into the chasing, and we come up with the mathematical model for that transmitting force, then we would be in the position to actually simulate that force and then further study that how that force behaves when we change the frequency of the excitation force, and how to reduce the effects of the transmitting force, or in other words, how to isolate the surrounding, that is the foundation or the chassis, from the vibration of the machine. So actually, as we discussed a number of times, that in order to study the vibratory system or analyze the vibrating system, first we have to model our real system. So again, we would be using the simple model, that is lumped parameter model, and for the ease we would uh, make or we would treat our system as 1 degree of freedom system. So we would model this engine, and also we would model this rotating machine. So here, let's say this is the lump parameter model, that is mass, spring, and damper system for the automobile engine. And here the this is the force of excitation, and the force of excitation is general harmonic force. The spring and damper is connected to the mass of the system, and at the same time they are attached to the frame or to the chassis. So and this is the actually response of the system. This is the excitation, and this is the response of the system. And here you see the lump parameter model for the machinery which is vibrating due to rotating unbalance. So we have the mass of the machine, and this is actually, let's say, the unbalanced mass which is actually on the rotor, and because of which we have the vibration. So because of that, we would have an excitation force which would be actually function of time, and it would have frequency omega, which is actually the speed of the rotor. And this is the response of the system. And again, here we are taking all of the elasticity of the system into this spring, and all of the energy losses into this damper. And this represents the foundation. So the question is, what is the force which is transmitted to the foundation or to the chassis. If we look here, actually the spring, one end of the spring and damper is attached to the chassis or to the foundation. So actually when the system is vibrating, when the mass is vibrating, so actually a spring, we would have spring force and damper force, and these forces would be on this end because this end is attached to the mass, and the same forces would be actually at the support, because the support is actually holding the um, spring and the damper. So that force, the spring force and the damper force, would be acting on the foundation, and because of that, actually because of that, the spring force would be transmitting, it would be transmitting into the foundation, and similarly the damping force. So meaning that the transmitting, the force which is actually transmitting into the foundation, it would be the summation of the spring force and damping force. So in order to find out the force which is actually transmitting into the foundation, so we have to make the free body diagram of our system. This is the free body diagram. So we have the mass, and on the mass we are showing all of the forces. So let's say at that instance the mass is moving in the upward direction with the displacement x of t, which is shown in this direction, and at that instance the excitation force is actually acting in the upward direction. And in case of harmonic excitation, the excitation force would be F naught cos omega t, and in case of rotating unbalance, F naught, instead of F naught we would have m e omega square sine omega t. If the mass is moving in the upward direction, in at that instance the spring would stretch, it would expand, and it would pull the mass in the downward direction. So the spring force would be in the downward direction, and its value would be k times displacement, that is kx. The damping force is always opposite to the motion, so it would be in the downward direction, and its value would be c x dot, where c is the damping coefficient. X, the steady state response, we if the excitation is harmonic, the response of the system would be also periodic and sinusoidal, and we could mathematically write that displacement as x steady state of time is equal to capital X cos omega t minus phi. Capital X is the amplitude of the displacement, and phi is the initial phase difference between the excitation and the response. Similarly, if we differentiate this displacement, we would get the velocity at which this mass is vibrating. So x dot of t is equal to minus omega x sine omega t minus phi. Transmitted force to the foundation, because spring and damper is connected to the foundation, so the forces which are actually acting on the spring and damper, that those two forces are actually going into the foundation. So the transmitted force would be the sum of the spring force, which is kx, plus the damping force, which is cx dot. So putting for x here, so we would have k. K is missing here, but remember that there is k here. So k um, capital X, and putting for writing for this x, x is x of t is equal to capital X cos omega t minus phi. So k time capital X cos omega t minus phi, and putting for c is already there, and putting for x dot, which is minus omega x sine omega t minus phi. So we would have minus c omega capital X sine omega t minus phi. So we have this mathematical model for f of t, transmitted force. But remember that this force here, this equation is for f transmitted force with respect to time. So it is the transmitted force as a function of time. So we are interested in finding out the magnitude of this transmitted force. This is actually the equation. This equation for the transmitted force is actually with respect to time. It is changing with time, and we want to find out the magnitude of this transmitted force. For that, we would go back to the slides which we have already discussed. That is the relationship between displacement, velocity, and acceleration. If this is our displacement is harmonic, x of t is equal to a sine omega t. Then if we plot this mathematical model, so along the vertical we have x of t, whereas along the horizontal we have the independent variable t. And if you plot this, we would have this plot where a is actually the amplitude of the response or displacement. If we differentiate this equation with respect to time, we would have a omega cos omega t, and if you plot this, we would have this plot. And the amplitude, this is amplitude of the velocity of the mass, which is omega a. If we again differentiate this with respect to time, we would get the acceleration. So x double dot of t is equal to minus omega square a sine omega t, where omega square a is actually the amplitude of the acceleration. And if we plot this mathematical model, so we would get this plot here. This is the acceleration with respect to time, and this and along the horizontal we have the time. If we look at these three plots and also these three mathematical models, very simply we could understand that the velocity is leading the displacement by 90 degrees, and similarly the acceleration is leading the velocity by another 90 degrees. Or if we see that the uh, phase difference between the displacement and the acceleration is 180 degree, and they are out of phase. You could easily see that here. If you look at the amplitude is plus, here the amplitude is negative. So what does it mean? It means that both are actually in opposite direction, meaning that they are out of phase. These two signals are out of phase. We could also see here the peak of the displacement is on the positive side, whereas the peak of the acceleration was on the negative side. So these two signals are out of phase. And here you could see that the displacement here is zero, whereas the velocity is maximum. What does it mean? That the phase angle is 90 degree. The phase angle between the displacement and velocity is 90 degree. So we already discussed that the velocity would lead the displacement by 90 degrees, and the acceleration would lead the velocity by another 90 degrees. In other words, the acceleration would lead the displacement by 180 degree, and they are out of phase. Remember that they are out of phase. All three of these are actually vectors. Displacement is a vector, velocity is a vector, acceleration is a vector. So we could plot these three vectors. So let's say this vector represents the displacement. This is capital X. So the velocity would be at an angle of 90 degrees to it. So the velocity is at an angle of 90 degree to the displacement. And acceleration is actually out of phase to the displacement, or it is at 90 degree to the velocity. So acceleration, we are making the acceleration vector, which is out of phase to the displacement, and it is at 90 degree to the velocity. So we have already discussed this. So now here we have the force vectors. What are the force vectors? The force vectors are actually the spring force, damping force, inertia force, excitation force. So we could also actually plot those vectors, and we could add those force vectors. So let's say here what we are doing, we are adding the force vectors here. So this is what, this is the displacement vector. Let's say this is the displacement vector, capital X, and we know that the spring force is actually opposite to the displacement. So the spring force is actually, the magnitude of the spring force is K times capital X. K is the stiffness of the spring and capital X is the amplitude. It is the amplitude of the displacement. So this is the maximum maximum spring force, which is K times capital X, and it is opposite to what? It is opposite to displacement. So we know that. So I'm plotting that force Kx, and we just discussed that the damping force is at 90 degrees to the spring force. So I'm drawing the vector, which is the damping, which is representing the damping force, and it is at 90 degree to the spring force, and I am adding these two vectors. We are adding the vectors by head and tool, by head and tail method. This is the graphical method by which we could add the vectors. We already know this, you are studying this in your statics course and in other physics courses. So adding, we are adding these two vectors, and the third vector is actually the uh, acceleration vector, or inertia, inertia force. It is the inertia force, and the inertia force is actually m omega square capital X, and the inertia force is actually because of the acceleration. And adding this by head and tool method, by head and tail method, so this is actually the acceleration force. And the resultant, if we join the tail of the first vector with the head of the last vector, then what we would have, we would have the resultant, and the resultant in this case is actually the force, the magnitude of the excitation force F naught. So actually by graph we have the vectors, force vectors, we have the kinematic so vectors. So actually here just we are adding all of the forces in order to get what, the amplitude of the excitation force. Similarly, because we just discussed that the spring force and the damping force on this side is actually in going or transmitting into the foundation. So similarly, we could add these two forces, that is the spring force and the damping force, in order to get its resultant. And that resultant is what? That resultant is actually the force which is actually transmitting into the foundation. Here on this plot, that is figure C, we are plotting only those two forces. So this is the spring force, and this is the damping force, because the damping force is at 90 degree to the spring force. So we are adding these two vectors by head and tail method, and at the end the tail of the first vector is joined with the head of the last vector in order to get the resultant. And here the resultant is what? The resultant is the transmitted force. And this is a right angle triangle, so we could now apply the Pythagoras theorem, because we know the spring force, we know the damping force. Then by Pythagoras theorem we could find out the magnitude of the uh, resultant force. So the resultant force is Ft. Pythagoras theorem is actually what? The square of the hypotenuse is equal to the square of the base plus the square of the perpendicular. So here Ft is equal to under the root, the square of the spring force is kx square, and the square of the damping force is c omega x whole square. We could take x common, which would be x square here, and if it is x square, then we could take it out of the under root sign. So afterward we would have the transmitted force. This is the magnitude of the transmitted force is equal to capital X under the root k square plus c omega whole square. So just by using the uh, vector summation through graphical method, we come up with the magnitude of the transmitted force. So the magnitude of the transmitted force F of t, F transcript t is equal to capital X under the root k square plus omega square c square. And we already discussed in case of the forced system, forced vibratory system, and the system which is vibrating due to rotation unbalance, we come up with the mathematical model for the this displacement. And that mathematical model was capital Xk by F naught in case of harmonic excitation, and in a case of rotary unbalance, it was capital X k by m e omega.